Testing, testing, 1, 2, 3, testing, testing. Good morning, everyone. Good morning, everyone. I have my microphone turned on today, which is good. Is there any way to see what we did wrong on the assignments? Yes. If you go into the assignment page on Jupyter, there will be a blue button that says Fetch Feedback. If you click that, you'll be able to get your feedback on your assignments, which specifically tells you which test cases you passed and which ones you did not. So that is a good way of going about it. We have 43 people tuning in today. Hopefully that number goes up a little bit. I don't expect it will go up too much. Normally attendance is low the day after a test, or the first class after a test. So, it's also reading week next week. Everybody getting ready for those vacations to the Bahamas that they can't take this year. Yay! Fetch feedback doesn't work. Well, that is something that I need to talk to Mark about then. What about the people who did the assignments offline? Well, in order to actually mark your assignments that you submit through Avenue, we actually have to upload them to Jupyter anyway. So they end up in the Jupyter system. All right, perhaps, I don't know, I'll talk to Mark about it. We'll make an announcement about it. I shall talk to Mark about it. Let me just write that down. And we'll get that squared away. So the test, though. How did you guys find the test? Was the test too easy? Was the quest way too hard? Was the test, was the porridge too hot, too cold, or just right? Would you guys say? Traditionally, the class average on the first midterm is exceptionally high, in the 100% range. So, yeah. It was good, says Lacey. Okay. Lacey says it's good. I'm going to assume that everybody else thinks it's good too. Nah. Yes, that's how this works, right? A bit difficult. Took the time you said it would. Oh, good. I took the time. Yeah. Okay. Manageable. Wasn't too bad. Okay. See, it's actually good if the test is a little bit difficult. Like, not so... Some of the porridge was too hot. Okay. It's actually good if the test questions are, a little bit on the hard side, because that means that they're actually pushing your understanding a little bit. And that's part of the purpose of the test. It's not just regurgitation. It's have you absorbed these concepts to the point where you can extend them into territory that might be a bit unfamiliar to you. In terms of educational psychology, you have what's called the zone of proximal development. I'm not sure how much they give you of educational psychology and whatever you're... Like, there are a lot of people in a lot of fields in this class, but essentially the idea is that you want to have a student almost always working within their zone of proximal development, which is to say, you don't want them doing too easy stuff that's too easy, because then that's just, sort of mindless repetition. Although there is a certain purpose to mindless repetition, it cements concepts. Good to mindlessly repeat your times tables, for instance. And you don't want people doing stuff that's like way beyond what they can do, because then, it's so difficult to get into it. There's sort of this Goldilocks zone between the two where it's like you're being pushed, but you're not being pushed too hard. But anyway, good. So the test wasn't bad. Okay, well, let's continue on with our lecture material then, because we've got a lot to do. I'll let you know right up front. I'm gonna skip the entire section on Spectre. This is like a section on a particular bug that can exist inside of computers, but it's fluff. It's filler. We don't have time. I'm dropping it, so you can assume that I won't test you on it. Although at this point you should have a pretty good idea of the sorts of things I test you on, specifically your ability to code. So, cool. All right. So, we left off talking about counters and accumulators. Most of you will have had decent practice with this with the test. So, a counter variable, when you're setting up a loop, is something that keeps track of how far along you are through the loop iterations. So if your loop is going through all of the elements in a data structure, like a tuple or a string, the counter variable indicates what index you're at. The accumulator variable is it's the variable that keeps track of the thing that will eventually be the result. So, for example, if you are keeping track of a sum, the accumulator variable is that sum. Every element gets added to the accumulator through each loop iteration. I actually remembered to bring up topic 3 this time around, or, bring up a document in which to do some coding. So, anyway, I won't belabor the point because we've already been through these slides. So, you can count up, you can count down, you can even count sideways. The main thing, though, is that in whatever direction you're counting, you have to eventually hit the loop condition. It's always recommended when you're using loops to use greater than or less than as loop conditions rather than using exact equalities. And we'll see this. This will apply to recursion as well, which is a topic that we'll be seeing soon. So imagine a scenario, right? Imagine you have a sequence where you're adding up 0.5, 0.1, 0.5, 1.5, 2.5, 3.5, etc., etc., etc. Now let's say that your loop condition is something like x is equal to 10, right? This loop condition will never be hit because, the sequence of numbers will get to 9.5. It'll go past 10 to 10.5. It'll never actually hit this. And what will eventually result is that you will get an infinite loop. So I don't believe I've talked about infinite loops a lot yet. So let me digress for a moment on the subject of infinite loops. So, if you've ever been in a situation where a program stops, becomes completely unresponsive to input, in Windows it's like this program is not responding. It can happen for a couple of reasons. Normally, like if you're loading up your copy of Civilization 4, which is the best Civilization game, then, while that game is loading, it may go through a brief period where the Windows operating system considers it to be unresponsive because it's loading, because it's not being responsive to input, because it's doing something else. That's a different scenario. Sometimes things are just loading, but sometimes it's like, nope, this program has just stopped. It's dead. It has died, and it dies unexpectedly. 9/10 of those are caused by what are called infinite loops. So what is it? As the name implies, an infinite loop is a loop in which the exit condition is never reached. It's a loop which never terminates. Never terminates. This means computers are pretty dumb, right? The thing about a computer, they're not intelligent. people think computers are intelligent. Computers are not intelligent. People who write programs are intelligent. They can use the tool that is the computer to do intelligent things, but the computer itself is the dumbest thing in the world. All a computer can do is execute the instructions you give it sequentially. So, if you have a loop, I is equal to 0, while I is less than 10, print I. So, there are two main ways that an infinite loop can develop. The first way is not doing anything with the counter variable between executions of the loop. The way that this loop is written right now, let me blow that up for you guys a little bit. Is that big enough? I think that, maybe I can blow that up a little bit. View, no, tools, nope. Text editor preferences. That sounds more like it. Font. We'll give you a bit bigger. No, that's too big. Yep, that'll be fine. All right. There. Maybe that's a little easier to read. So, right now, each time the loop is executed, I, the counter variable I, is not modified within the loop. So, it'll just repeat 0 infinitely. And we can see this if we, very unwisely, decide to execute topic3.py. So be careful when you're doing this sort of thing, because you can actually... it used to be the case in certain operating systems you could actually crash your computer entirely by doing stuff like this. But me, I'm pretty quick on the cancel instruction hotkeys. So there. I terminated with keyboard interrupt. So essentially, all it's doing ever is printing 0. And you can see it prints a large number of zeros. That's because I is not being modified between loop executions. So if we say I plus equals 1, you can see we print you can see the value of I changes between the loop iterations. Since we start low and we are adding, we are traveling in an upward direction, which means we want an upper bound to the counter variable that designates when you're out of the loop. So, but you can see that you can just as easily miss a loop condition if you use equality as missing a loop because you sort of used an equality operator inside of a loop condition. That can cause, like, it's if you're just using integers, it's not as big a deal. But if you're using floating point numbers at all, you want to avoid equality comparisons anyways, like in all cases. So, let me save that. Oh. Huh? Well, at any rate, it's interesting. I wonder why that's happening. Maybe I have to do this. It's interesting. I wonder why that's not working. Any rate, probably somebody in chat will be able to tell me why that's not working. So you can just as easily miss a loop condition by passing over it, as that's equally a case that you want to avoid, as well as forgetting to increment the loop variable. And you'll probably see me forget to do that a couple of times, because it's an easy thing to forget how to do. And part of this is, like, we are trying to yeah. Oh my god. Nope, I'm sorry. No, I'm sorry. 4 is the best. In later Civilization games, they have exchanged mathematical complexity for descriptive complexity. I can finish a game of Civ 4 in 4 hours. It takes at least 30 hours to finish a game of Civ 6, and that's just too long. I understand that's the trend in strategy games now, that they just take forever, but it's a bad trend. There. So, alright. No, I'm not going to change the font to Comic Sans. I could, though. I could also change it to Papyrus. Yeah. Anyway. So, yes. So anyway, so infinite loops. You want to do your best to avoid them. If you get one in Jupiter, then what happens is in those little square braces, you'll get a star character, which means currently executing, and it's like, wow, it shouldn't take that long to execute this stupid little code. So if you go to your toolbar at the top of the Jupiter interface, there's a stop button, so you'll want to hit that stop button. Cool. So, here's a question. With this code here, what does this code do? Sum of t, I is 0, sum is s. While I is less than the length of t, s plus equals t at I, return s. What is the output? I will give you a moment to enter your answers into the chat. Ha! Make sure to never play Stellaris. You know, I actually really like Stellaris, but I can only play it on, like, the fast mode. Stellaris is good, but the unit... I have a problem generally with these 4X games that the unit unit manipulation is just so fiddly. Yeah, so... In this case, if you answered D or C, then that would be correct. Although C is kind of iffy. So, because we have forgotten to increment I inside of this loop, this is an infinite loop. So, it is true to say that it doesn't output anything. Whether or not it's an error, that depends on what you consider an error to be. If you consider an error to be the computer gives me an error message, then that's not an error. An infinite loop does not produce an error message. However, an infinite loop is a class of error because it is not what you want the computer to do. Pardon me. So, yeah, it's an error if you consider the computer not doing what it's supposed to be an error, which I would say is a fair definition of an error. However, if you're waiting for an error message, you'll never get one. So C is kind of like, but D definitely. All right. So, infinite loops. I already talked about a lot of this. There you go. So if you've got an infinite loop, you'll get the star. You'll get the star character right there. A couple of ways to deal with it. You can hit that stop button right there. Or you can actually go, you can go to the control panel and restart the server as well if the stop button doesn't work. Oh my gosh, I screwed up my zoom. There we go. All right. So, one other thing to note. Typecasting. So, it will often be the case that you have a string and you want a float, or you have an integer and you want to make it into a string. you can use functions to convert things between different data types. So, for example, Python 3 interpreter, if I have the string 1.34 and I wish to convert it to a float, I merely call the float. You call the type name as a function name on whatever it is you want to convert. If we then subsequently convert that to an integer, you get 1. However, I think if you try to do it to int directly, it's like, yep, can't convert. So, because this string does not interpret as an integer cleanly because of the decimal point, you can't actually convert it to an integer. So this is actually a very useful thing to know. The conversion functions will fail if the thing you're trying to convert is not convertible, if that makes sense. For example, what is the integer interpretation of potato? It is nothing. Potato is not a base 10 number. What about in base 32? Then it does. So we'll get into how and why this works in a later lecture, but essentially this is interpreting each of these characters as a number with a place value above 10 in a base 32 system. But anyway. So yeah, you can convert types. This is especially useful when you're dealing with data structures, because you can do this with data structures too. So let's say we had a tuple that was 3, 4, 5, 6, 7. Sure. If we wish to convert it to a list, there we go. All we have to do is that. If we wish to convert it to a string, then notice it includes the braces and the commas and all of that junk. And if we have it as a string, can we convert it back to a tuple? Oh, well, if the professor could spell things correctly. Yes! But notice that each character has been put in the tuple. So, yeah. Not a direct or clean conversion. So this is an example where the operation is not reciprocal, which is kind of cool. All right. So if statements. We already know some stuff about if statements. So we've had these two constructions of if statements so far. Now we're going to talk about the elif, or the else if. So if you want to chain multiple conditions together, you use what is called an elif, or an else if statement. So, let me just get rid of this. So let's say I is equal to 0. If I is equal to 1, do stuff. Elif I is equal to 2, do other stuff. Elif I is equal to 3, do other stuff. Else do the final stuff. So you know, you can get the idea. This also works with inequalities, incidentally. So the way that it works is that it hits the first condition. If that condition evaluates true, then you execute whatever the first set of statements are. If this condition comes out false, then you pass into this one. You evaluate this condition. So with an else-if structure, only one of these branches will ever be executed, depending on what the conditions are. And else only executes if all of the other conditions have come out false. For those of you who know other programming languages, this is how Python has chosen to do switch cases. So you don't actually have switch cases available in Python. You have to use else-ifs as well, and I know that's clunkier, and I know there's a reason for switch statements, but this is the way that they've decided to do it because they figured that switch cases were redundant given that else-ifs exist for some reason, even though they don't technically really do the same thing, really. Yeah. So anyway, let me see if we have any questions. Nope. Okay. Yeah. So, here is a question. Here's a function that determines whether or not a number is even or odd. So, if you take the modulus of something, if you take the remainder of integer division by 2, if the remainder is 0, then the thing is even. Otherwise, it's odd. So, print even odd of 5 would return odd, and print even odd of 10 would return even. So, just for example, 5 modulo 2 is 1, 10 modulo 2 is 0. Write a function that determines whether a number is divisible by 2, 5, or 10. So we've got this divisibility function. Copy. Hopefully this works. Okay, I have to fix the indentation, but that's okay. That's okay. Boop. Boop, boop. Boop. Boop, boop. Boop. Boop, boop. So, if we print divisibility of 5, then let's see what happens. There we go. By 5. Good. So it evaluates if 5 modulo 2 is equal to 0. It's not. Then it evaluates this one. So it says by 5. Notice that, well, anyway. So what about 10? By 2. So with 10, it evaluates if n is divisible by 2. And since it is, it returns by 2. It does not worry about whether or not it's divisible by 10. It only executes the first... It only goes as far as the first condition that turns out true. Since that's mod 2, then that's the case that we go with, and that's the resulting output. Despite the fact that you and your human brain may think, well, but this is a better fit for the data. It's like the computer doesn't care about fit for the data. The computer has no concept of what fit for the data even means. Unless you teach it that, right? Computers only execute instructions. So, there you go. Can I explain a switch statement? I can do it quickly. So this is a common construct in like Java or C or any other, literally every programming language other than Python and maybe Haskell. So how you write it is switch I. It would be, sorry, we're in curly brace land now. Case 0. No, I think it's. It depends on, sometimes the syntax is one way, sometimes it's the other. I think it's actually colons. Do stuff, break, case 1, do stuff, break. So, with a switch case, you specify what the variable you're switching is, and then you have each case of what that variable might be, and you can also do an otherwise case down the line. The thing about switch cases, though, is if you don't include a break statement inside of a switch case, then execution will fall through this case into the next one until it hits a break statement, because it's the break statement that gets you out of the switch case. But yeah, that's what a switch case is. Python doesn't have them, so don't worry about it. Doop, 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 doop. Why do we always start with statements like I is equal to 0, etc.? Is that a placeholder? No, that's not a placeholder. if you do not include it, then I is not declared. So, like, if we were to do I is less than 10, you know, I plus equals 1, print I. Let's say we wanted to run this loop without having declared I up front, right? Name I is not defined. So you can't use a variable before you've declared it, even in Python. So what that does, the purpose of this statement, I is equal to 0, is it creates the variable called I so that the variable I may be used later on. It also, the equals 0 part, that gives it an initial value. I don't have to do 0. I could do something like 4 or 5, right? And then if once I did this, it would start from 5, right? You don't have to make it 0. It can be anything. It's just 0 is often convenient, right? It often works out that 0 is the thing you're going to be starting at, sort of for the reason that, you know, for example, tuple indexes start at 0, so 0 is often the thing you're going to be starting at, you know, sort of regardless. But yeah, no, it's not a placeholder if it is critical. That line is mission critical. I did not include it for my own amusement. It is absolutely critical that it be contained inside of the program. Cool. Are we going to learn about hexadecimal? Yes, we are. As soon as we get there. That's in the next topic, I'm pretty sure. So, anyway, yes. I'm not going to do the quizzes. So, the quick thing, if we exchange the conditions here so that 10 is evaluated first and 2 is evaluated last, the results can be easily predicted. Well, I have to change what the message says as well. Again, the computer will execute anything by 10. So when you exchange these, by 10 is the one that turns out because that's the first case that evaluates to true. Fine. The other thing that you can do is you can nest if statements within each other. So let's say rather than invert the order here, we can include another if statement. If n mod 10 is equal to 0, then we return by 10, else we return by 2. This essentially has the same effect. Meow. If you come up here, I'll put you on the stream. Maybe she'll come up. Anyway, so in this case, what happened? This is a different thing from an else if, right? If n mod 2 evaluates to 0, then it evaluates this one. If this one evaluates true, then it has evaluated both of these cases to come out true, so it returns 10. Another way you could do this is you could say 5 here, because 10, in order for something to be divisible by 10, it has to be divisible by both 2 and 5, which are the factors of 10. But anyway, that's fine. I won't belabor the point. Skipping the Spectre stuff, because it doesn't matter. Very quickly, I guess, Spectre was a bug that existed inside of certain CPUs, which could happen if you loaded and unloaded data into cache memory in a particular manner, and basically it has to do with the CPU would predict what the results of if branches were, and it would somebody could steal that data if they manipulated things exactly correctly. It was a huge vulnerability, but it's also kind of complicated, and we're just going to move through it. If you like, read the Wikipedia article. So let's talk about linear search. We're going to get into some algorithm stuff. So right now we're going to describe an algorithm and then implement it. So when I say this is algorithm stuff right now, I mean something more like this is your dipping your first toe into the vast swamp that is algorithms as a subject. So, like, you can take second year, third year, I think the comp sci guys have to take it in first year. Shush! Meow! Oh my god, that cat. Oh my gosh. Alright. So, linear search, the object of the algorithm, is to go through a set of, go through a data set, like a tuple, and see if a certain value exists within that data set. So, can you guys hear that cat? I can hear that cat. So, anyway, so with linear search, there's sort of the brute force approach is to basically just check every element in the tuple or list or whatever and see if that is identical to the element that we're looking for. Call that E. So, I is equal to 0, while I is less than the length of T. I plus equals 1, just get that out of the way. If T at I is equal to the element we are looking for, return true. If we manage to execute that entire loop without having returned true, we can return false. There we go. So, if we print, let's say we've got a tuple T is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If T, let's lin search the tuple T for the element 14. And I have a syntax error. There. False. That is correct. How about 4? Does 4 exist? It's true. So this is a way of searching, right? Linear search. In Python, you can actually just you can ignore all of that and do the following: return E in T. Has the exact same effect, because in Python you have the there, you see, you got it true. In Python, the in operator already automatically, like, linear search is already the purpose of the in operator. So if you need to search things, this is the fastest and most efficient way of doing it. However, we're breaking this guy open and taking a look at the guts, because it's important and informative to learn how computers actually do these things. So, yes. We can also do this with characters and strings. So, Python being Python, we can also do, you know, hello world, and we can look for the character E. And it's in there. Yeah. The other thing that you can use is the indexing function. So some variants of this return the index of the found element, which, as this one does. So this guy, this is a more roundabout way of doing it. But essentially what's going on here is, first of all, they've baked in the condition for correctness into the loop itself. So rather than having an if statement here as well, one thing that you can do is you can put that right here. And t is equal to I. However, the trick with that is that once, if you have done that, after the loop has finished executing, you have to distinguish between whether you're returning true or you're returning false. So sometimes with people, they don't like to have return statements in the middle. They always want to have the return statement at the end. I'm not as strict about that personally. Like, when I'm programming, I'll just put my return statements wherever the heck I please. But, you know, you can see the argument for it. The more return statements you sort of fit into the middle of the code, the more the code looks like spaghetti code, which is probably a term you've never heard before. Spaghetti code is is code that you don't know where it starts and you don't know where it stops. It's like being handed a plate of spaghetti. You can see all of the strands of the spaghetti, but you can't tell where one strand ends or one strand begins. So generally speaking, in programming, we like to have all of our spaghetti noodles laid out flat so that we can tell where the beginning and the end are, because then we can hook them together much more easily. But again, for something this short, it doesn't really matter. But yeah. Yep, this is the version that I did, which is return the value immediately. The other advantage of returning immediately is that it minimizes the execution of redundant statements. You can also use break statements. So I showed you what a break is in the context of a switch case, but you also have breaks with respect to loops. So if you say break, what happens is that the loop is immediately terminated regardless of what the loop condition says. So we can say, up at the beginning, if this condition, there we go, then break. So start at 0, go, 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 until t at I is equal to e, then we break the loop. Execution immediately jumps then to the if statement, and then we do whatever the if statement says. Break statements are not used a whole bunch, but they're a good thing to have in the toolbox. The other thing, the other construct that you have is continue. Continue jumps you to the next iteration of the loop, regardless of where you are in the loop. These things end up looking a lot like gotos, though, and we generally like to avoid the use of gotos. So yeah, you can also just break the loop when you hit the condition, as demonstrated. So there you go. Linear search. Cool. Any questions? Yes, good programming is raw noodles laid out, not in a clump. You don't want clumpy noodles. Show me on the cam. Yes, okay. There she is as she's on the couch. 1 second. Honk. There we go. Oh. Hello. There is the kiddo. Hello. Say hello to the stream, kiddo. Yes. Yeah, cool. All right, kitten. You and me are going to do some more topics. We're going to talk about for loops. The reason that we didn't do that with a for loop is because we haven't covered for loops yet. But now we are going to cover for loops. So, for loops are an entirely different thing in Python than they are in other types of programming languages. In C, a for loop is really just a while loop that has a bunch of the stuff that you would put on other lines inside of the for loop itself. So that's not how things work in Python. In Python, in order for a for loop to work, it requires an underlying data structure. So it's absolutely 100% necessary to have something like a tuple or a string or something like that. And if you don't have one, then you have to generate one. And we'll get into how you can generate these types of things on the fly. So, this is what a for loop does. It goes through the data structure, one element at a time. It creates a new variable that assigns it assigns a name to each of those elements. You can then deal with that element in the loop by that name, and then when it runs out of elements in the data structure, it just terminates. You don't have to worry about setting a condition. So in Python, for loops don't have conditions. The condition implicitly is, I'm going to do this for every element in the data structure, and then I'm going to stop. So, very quickly, or not very quickly, here is an example of a for loop. There we go. For character in the string hello world, print character. There we go. Let's see if this works. There you go. You can see every element has been printed. So that's pretty compact, right? If you wanted to do that with a while loop, you would have to, A, have the string separately designated. B, you would need a loop indexing variable. C, you would need the condition itself, so while I is less than the length of s, you would have to remember to increment that, and then you could print s at I. So these two, you can see that this guy is 5 lines of code, whereas this guy is 2 lines of code. So it's just easier. And because you're not manually responsible for remembering to increment the loop or remembering to make the condition correct, it's actually much more difficult to get a for loop into an infinite loop than it is a while loop. While loops are more dangerous because you have to know what you're doing a bit more, or you have to be more cognizant of what you're doing. So that being said, it is definitely still possible to get a for loop into an infinite loop. If you add an element to the thing you're looping over, then the for loop will never terminate because it'll always have, like, the size of the amount of remaining data structure to go through never decreases if you add one element to it every time you iterate the loop. Generally speaking, in for loops, it's kind of bad form to modify the data structure that you are operating over inside of the loop itself. But, you know, for that sort of reason. See if there are any questions. Can the cat do for loops? Cat time. Can the cat do for loops? I don't know. If for loop means sleep, then yes. So, so yeah, that's for loops, essentially. But, of course, let's hammer these things silly. So, for example, this is a similar example to the one I did. These are equivalent constructions. Actually, technically speaking, this the one that I did before, if you want it to be exactly the same, then you need 6 lines here. Notice I'm printing from the string directly, but I'm missing the functionality of the for loop where the C variable is implicitly assigned whatever element of the string you're on in between. So if I wanted an exact correspondence, what I would do is I would add one line which assigns s at I to C and then print C. that is actually, this is the full everything that this is an exact duplication of everything that the for loop is doing, if that makes sense. So it's important conceptually to get this idea that this C variable is being assigned every element in the data structure in succession. That's a sticking point that people have with for loops some of the time. So in this instance, we are manually doing that assignment. We are doing that explicitly. In the for loop, that is being done implicitly, just like when the actual parameters are assigned to the formal parameters in a function implicitly. This is also implicit assignment going on. So yeah. I guess next time we will finish off for loops and hopefully get on to topic 4. But yeah, that's all good. If you have any questions, if you have any questions, please let me know. I don't know. I don't know if that's I don't know if that's being disrespectful to the cat. Cats don't really care. Cats are all about their own business. They don't really care what you think of them. As long as the food is there, they don't really care. Could I go over lin search again? Yeah, I could do that. So with linear search, so the in terms, let's visualize it. So we have this tuple here, right? The thing that we want to do is we want to go through each element in the tuple sequentially, examine it, see if it's equal to the value we are looking for, and if it is, we return true. Otherwise, we allow the thing to go to the end, and if it didn't find the thing it was looking for, it returns false. This got a little bit complicated because of all of the slides, but essentially, in its most pure form, it looks like this. I don't know why I always like to leave a space after a loop. I just think it looks cleaner. You can do whatever you like. So we start with our index at 0. We continue as long as I is less than the length of the thing we're searching. If the index at the thing we're searching is equal to the element we're looking for, then we return 2. Then then we add I. Add 1 to I, pardon me, which moves us to the next thing. We can actually also do this with a for loop. Let me just do this with a for loop, just to illustrate for loops. So, for little t in big T, if little t is equal to the element, return true. Otherwise, return false. And that's the same thing, but it uses a for loop instead. Ah, yes. Is it possible to make A3 due on the weekend of reading week? Yeah, that seems like a reasonable request. Next week is reading week, so, yep. Ha. Yeah, okay. Yeah, okay. I will make an official pronouncement. I am making this official pronouncement. Assignment 3 will be due the Sunday of rating week instead of this Sunday. I'm going to push it back by 1 week. I'm surprised it wasn't already like that in the calendar. So, A3 push back a week. I followed through on that magic 8-ball question, eh? That one, hopefully that one wasn't the difficult question. Cool. You're welcome. I'm, firm but fair, I like to think. I like to think that my policies are, yeah, good. I like to think that my policies are firm but fair. Yeah, like, when will the test marks be out? Probably Tuesday. Probably Tuesday. My camera froze again. Gosh darn it. Seems like I get like 50 minutes out of it, and then it freezes. At least I didn't freeze on a stupid face this time. My goodness. There. Now, question. Am I using this mic? Nope. Alright. Yep, the sound quality probably took a nosedive too. I don't know why it does that. Yeah. Nope. Don't even know why I'm bothering fixing. Yep, there we go. Cool. All right. Any other questions? You guys have class to get to. You guys probably have class to get to, so. What was our peak viewership today? Around 80, huh? 83. Yeah. That sounds about right. You know, that'll never actually... That probably won't pick up. It's interesting. It's actually kind of funny. Once the class size gets large enough, the number of people who watch in any given... who are watching any given lecture, that's actually an exponential decay. Like, it's so cool. It's like, you know... Tell me math isn't real. Exponential decay on viewership. You know? Cool. Alright, well, I guess that's everything today. Take her easy, folks. Have fun. Have a good week. Math be with you. Etc., etc.